Now, what do you mean by double-ended clipper? As the name says, double-ended, in the sense the clipping should happen in both the ends of an input waveform. Okay, so a double-ended clipper shapes the positive half cycle of the input as well as the negative half cycle of the input. All right, so double-ended clipper shapes both positive and negative half cycle of the input. All right. Now the question is how? How? So far, whatever clipping circuits you had seen were either shaping the positive half of the input or the negative half of the input. But using a double-ended clipper, we are supposed to shape both the halves of the input. So any solution can you provide? How are you going to shape both the half of the input? Any solution? Is it striking your mind? Can you propose a solution? How can we do it? You can type your answers. Okay, you can type your answer. How to shape both the halves of the input?
Using two diodes with opposite.
All right, correct. So using two diodes, as you have rightly pointed out, using two diodes, it is possible to achieve a double-ended clipper. Okay. Now, how are you going to place those diodes? That's my second question. Okay, so one of you told me two diodes you can use, which is absolutely perfect. Correct. Now, how are you going to place those diodes? Okay, now for this, you will have to, go back to, the previous class. In the previous class, you have studied about positive clipper and negative clipper. Okay. Negative clipper. Okay. And remember, the positive clipper as well as the negative clipper were studied independently. Okay. In case of double-ended clipper, what we do is we do kind of fusion. Okay. We use a positive clipper as well as negative clipper. So double-ended clipper is nothing but a combination of positive and negative parallel clipper. All right, so that is what all we need to do. Okay, we need to connect a positive clipper as well as a negative clipper. Okay, fine. So let's look at the circuit diagram. Circuit diagram. Okay. So in the circuit diagram, first you have to draw the source. Okay. V in having a maximum voltage of Vm. Okay, and then comes the current limiting resistor Rs. Okay. And then comes the diodes. Okay, so you have first let us achieve positive clipping. Okay, let's say this diode is made up of silicon. Okay. And here you will have the negative clipper. Okay, negative clipper. So let's say this is also made up of silicon, and this is where you are going to absorb your output. Okay, minus plus. Okay, so basically, what are you seeing here? What are you seeing here? So in this particular circuit, as you can clearly observe that this end of the diode, okay, this part of the circuit, talks about positive clipping. positive clipping. So this part of the circuit drives your shaping of positive half of the input, and the other, diode leg determines the shaping of negative half of the input. Okay, it determines negative half of the input, or I can simply say that it does negative clipping. Negative clipping. So in tandem, they are working, right? You have a positive clipper in combination with negative clipper. All right. So first, let us, construct the equivalent circuit. Equivalent circuit. Okay. If you have understood the working, you can go ahead. Okay. You can proceed with the analysis part. So let me redraw the source. Input with the maximum voltage value of Vm, series resistance Rs, followed by the diode. So the diodes are made up of silicon material. So what I'm going to do is I'm going to draw its equivalent circuit. Okay, so this is my ideal diode D1 and its corresponding barrier potential. Okay, plus minus. All right, so let's call this as VK1. VK1 is 0.7 volts, doesn't matter. And in the second leg, you have once again the equivalent circuit model of the diode. Okay, so upper side is cathode, lower side is anode, as indicated. And then you will have the corresponding barrier potential, right? So to the anode terminal, we should connect negative terminal of VK. Right, so this is minus and this is plus, and this is VK2, and this is where you are going to observe your voltage. All right, fine. So we have drawn the equivalent circuit. Now comes the analysis part. Analysis. So as I said in the previous class, whenever you have to do the analysis, you have to take once a positive half cycle and once a negative half cycle. So first let us consider positive half cycle. Okay. So let's say this is figure 1 and let's say this is figure 2. So positive half cycle. So what you have to do is in the positive half cycle, you put the polarities. Put the polarities. So upper side positive and lower side negative, right? And your source is trying to circulate the current in clockwise direction. Okay. And VK1 is trying to circulate the current in the anti-clockwise direction. Okay, fine. And if you look at your diode D2, okay, if you look at diode D2, if you can clearly observe that, see, anode terminal of diode D2 is connected to negative terminal, all right? And cathode terminal, if you look at, either it gets connected to VK through diode D1 or it gets connected to VI, okay, through RS. So for positive half cycle, if you inspect closely, D2 remains off. D2 remains off. For the entire positive half cycle, diode D2 remains off. Okay, and it is quite obvious, right? Because during positive half cycle, the shaping is going to take place in the positive half of the input. Okay. On the other hand, source comparison of VI and VK1 needs to be done. Because in the positive half cycle, Vi and Vk are of opposing kinds. Okay. Now the question comes: what happens, okay, when your input is less than Vk? Okay. So when your input is less than Vk, which source is dominating? Vk is dominating. Vk is dominating. Okay. So when Vk dominates, what happens to the diode conduction? Okay. This is your diode. And this is your Vk1. Okay. Plus minus. And this is your V0. Okay. So what I have done, I have removed the D2 part. Okay. D2 part I will remove. Okay, this is your D2 part. Okay, what we have done, we have removed. Because they don't come into picture, then why we need to retain it? All right, fine. So Vk is dominating. So what we can do, we can put the double tick here. So Vk is trying to send the current in this direction, and therefore diode D1 is reverse biased. Okay, reverse biased. So what do you mean by reverse biasing? Replacing the diode with an open circuit. Okay, open circuit. Diode is reverse biased. Okay, when diode D1 is reverse biased, what is my output? My output is my input. Output is in my input. Okay, so this is nothing but positive half of AC input. Okay, so that's my output when Vi is less than Vk. Okay. All right. Next, you go for the second comparison. What if when your input starts to exceed Vk? So when your input starts to exceed Vk, input is dominating. And when input, where to dominate your Vk1, okay, Vk1, what happens? Input forward biases the diode D1. So input is going to forward bias the diode D1. So what happens to the equivalent circuit? The equivalent circuit, looks something like this. This is RS. Okay. So diode is forward bias. So you need to replace it with a closed circuit. And then comes the VK1 level. All right. And then you will have your, the output. So this is RS, Vi. As you can clearly observe, output is nothing but VK1. So what is happening? Output is getting shaped at VK1 level, so which is nothing but DC value. So the output is limited at VK1 level. Okay, so that is what happens during positive half cycle. And negative half cycle, during negative half cycle, okay, basically the complementary action is going to take place. Okay, what had happened in positive half cycle, the same thing will take place in negative half cycle, but everything will be in an inverted sense. All right, because you are dealing with negative half cycle. Okay, so in the negative half cycle, you can change the polarity of the source. This is your RS. All right. So in the negative half cycle, what happens is that diode D1 remains off throughout. Right. So for the entire negative half cycle, diode D1 remains off, and diode D2 comes into picture. This is VK2, and this is where you observe your output. Okay. All right. So let us put the polarities for negative half cycle minus plus. Okay. As you can clearly observe that the positive terminal of Vi, it is connected to negative terminal of VK1. Okay. And positive terminal of VK1 is connected to the cathode terminal of D1. So if you look at the sense in which the Vi circulates current, you can clearly observe that, okay, your Vi is trying to circulate the current in anti-clockwise direction, okay, and Vk is also trying to circulate the current in anti-clockwise direction. So both Vi and Vk1 will open circuit D1. Okay, so D1 is reverse biased for the entire negative half cycle. Okay, so the diode D1 stays off for the entire negative half cycle. So you can just remove off, this D1 circuit. But source comparison comes into picture for VK2 because VK2 is trying to circulate the current in clockwise direction, right? So Vi and VK2 needs to be compared. Both these sources need comparison. Compare. All right. So again, when you say comparison, what we mean by comparison, the source termination, right? What if your input is less than Vk? Okay. And what happens when your input is greater than Vk? So this is the meaning of the source comparison. Okay, when your input is less than Vk, let me quickly redraw minus plus. Okay, anyhow, this part is open. Just draw it in dotted lines for your understanding. Okay, and this is the second leg of the circuit consisting of D2 minus and plus. Okay, this is your Vi. Okay, as you can clearly observe that the current directions are in opposite, right? So this is trying to circulate the current in anti-clockwise direction. On the other hand, Vk2 is trying to circulate the current in the clockwise direction. But we are assuming that at this, state, Vk2 is having more potential than Vi. So when Vk2 is having more potential, what happens? Vk2 will reverse bias D2. So Vk2 will reverse bias D2. So when Vk2 reverse biases, diode D2, what happens? Your equivalent circuit looks like this. Open circuit. And then Vk2 you will have minus plus Vk2. And this is V0 minus plus. This is RS. Vi minus and plus. So what do you get when you apply KVL? When you apply KVL, minus to plus Vi minus to plus V0 is equal to 0. That implies your output is minus Vi. So the negative sign simply indicates that your output is an inverted one. Okay, makes sense, right? Because your input is inverted, so quite obvious that your output will also be inverted in nature. Okay, so that's your the first set of comparison. Okay, in the second case, when your input starts to exceed, VK2 level, okay, your input dominates, okay, thereby forward biasing the diode D2. Okay, so what happens when the diode gets forward biased? The diode conducts, right? So diode conducts. This is your D2. Now you are replacing it with a closed path, minus plus. This is your VK2, okay? And then you connect your source, plus, okay, I'm so sorry. It's minus plus. This is RS, okay? And this is V naught. Okay. All right. So when you apply KVL, what do you get? Your output is upper side positive, lower side negative. On the other hand, if you look at the second leg, you find that upper side is maintained at lower potential and lower side is maintained at upper potential. So there is actually difference in polarity. So your output is nothing but minus VK2. Okay, minus VK2. So what is this? This is DC level. Okay, in the previous case, it was AC level because output is equal to input. This is AC level. All right. So you have analyzed the positive half cycle as well as the negative half cycle. So now what you can do is you can simply draw the waveforms. Okay, let's draw the waveform. Input, let us draw. All right. Then let us draw the output. Okay. Now, before drawing the output, what we have to do is we have to show the transition levels. Okay, transition level. So transition level will take place in the positive half cycle as well as in the negative half cycle. So for the positive half cycle, we have a transition level at VK1 level. And for the negative half cycle, we have the transition level at VK2. All right. So what you have to do is you have to draw the transition points. Okay. First, you draw the transition points from the zero crossover of the input, right? And then you draw the transition points from the respective threshold levels. You have a threshold level at VK1 and also you have a threshold level at VK2. Okay. Fine. So this is your input and this is your output. Okay. the maximum value is Vm, and the negative maxima is minus Vm. Okay. So when your input for the positive half of the input waveform, when your input is less than Vk1, output is output is equal to input. Okay, something like this you will get. Okay, output is equal to input. So thick lines you can draw. Similarly here. Okay. And when your input starts to exceed Vk11, your output is at Vk. Output is at Vk. Okay, this is for positive half cycle. And in the negative half cycle, once again, when your input is less than Vk2, your output is input. Okay. So till here, your output is input. Till here, output is equal to input. And once your input starts to exceed Vk2, your output is getting clipped. So the output is getting clipped at Vk1 level and at minus Vk2 level. Okay. So output is clipped at plus Vk1 level and minus Vk2 level. So output is your input is getting shaped in the positive half cycle as well as in the negative half cycle. Hence, it is called as a double-ended clipper. Okay, double-ended clipper. The transfer characteristics, let us draw. Okay. So let us mark the transition points. Vk1, okay, and this is Vm. This is your input. And this is your output axis. This is your negative output axis, negative input axis. All right. Similarly, in the negative half cycle also, you have to mark the threshold point, which is Vk2. Okay. And then the negative maxima is minus Vm. Okay, this is minus Vm, this is minus Vk2. Okay. And you also mark Vk1 and minus Vk2. All right. So first let us consider the positive half cycle. So in the positive half cycle, okay, you please look at the output. When your input is less than Vk1, when your input is less than Vk1, your output is AC. Right? Output is AC. So what you have to do, you have to draw a small square here, and since it is AC, okay, till Vk1 it is AC, so draw a straight line, inclined line. Okay, that's your AC. And the moment when your input exceeds Vk1, what happens? Your output becomes DC, and your output is fixed at what level? plus VK1 level. Hence, I'm limiting the positive half cycle at plus VK1 level. Okay. And the complementary drawing you're supposed to do in the third quadrant. So the negative half cycle, your input is negative going and your output is also negative going. So, the graph is found in third quadrant, because in the third quadrant, input is also negative and output is also negative. So till VK2, we have AC. We have AC. And when your input is greater than VK2, you will have a DC level. Okay. So this is what all about the transfer characteristics. Okay. So this is DC, AC, and DC. All right. So this is your transfer characteristics.